So in this video, I'm going to try and show that given a function that looks like this, we can get the same result for its derivative using both the product rule and the quotient rule. So I'm going to start by looking at the quotient rule because I think that's kind of the natural one to pick looking at this equation. And remember the quotient rule, I've noted it here. You're looking for a numerator and a denominator that have x's in it. And once you've got that, you can apply this equation to get the derivative. So let's start with that and then we'll come back and look at what happens in terms of applying the product rule to it. So we have our equation where a is equal to this, and we're applying the quotient rule, so that means that I'm going to say the top line is u and the bottom line is v to match up with the rule. So I'm going to do as a bit of a sidestep u and v and its derivatives, because that's what we need to substitute into the overall derivative equation. So if u is equal to x cubed plus 4, we can take the derivative by taking the, by applying, the power rule. So top number 3 times the front number, which is an implied 1, x, take 1 off the power, and the derivative of a constant we know goes to 0. So that's u dash completed. So v is equal to x plus 2. We want to take its derivative, again applying the power rule. Remember we have like a 1 here and a 1 out the front. So 1 times 1 gives us 1, x, take 1 off the power, and derivative of a constant we know goes to 0. So here, rather than writing this as x to the 0, we know anything to the power of 0 is 1. So therefore 1 times 1 is 1. Oop, I'll delete this little bit here too. Alright, so now we're at the point where we can actually go and calculate our derivative. So I'm going to call ours a dash, okay, and it's just a matter of subbing into this. So I'll write it out. Alright, and now let's pop into it. So u dash is 3x squared. V on its own is just, I'll get rid of this one to make it a bit less confusing. Just the x plus 2 minus v dash is 1 times by u, which is the x cubed plus 4. And it's all divided by v, which is the x plus 2 all squared. So we can do a little bit of cleaning, I guess, on this function. So let's say I expand out the brackets. I'm going to get 3x cubed plus 6x squared. And then here I've got a negative 1 times both of these terms. So it's going to become minus x cubed and minus 4. And I'll just leave the bottom line factorized. So here we can see we have a cubed and a cubed. So I can pop them together. And this would be my answer then for the derivative of the function a. So now what I'm going to do is go back and apply the product rule, and hopefully what we will see is that we get the same answer. So if we go back up, all right, I'll do it over in this bit. So product rule. Now to apply the product rule, we need to have two things that are multiplied together. Okay, we can see here. And this u and v function need to have essentially x's in them. So if we look at what we have for a to begin with, we don't really have two things multiplied together. But what we should be able to do is make it happen. So what I could do is put this bottom line, if I put it onto the top line, then we'd have two things with x's multiplied. So remember that when we do this, I'm going to bracket this off. All right, this is like the same as x plus 2 to the power of 1. All right, it's like that implied 1 again. So if we shift it to the top line, we change the power on it. So it ends up with a negative 1 on the top line. Now what we can see is we've got the case of two things multiplied together. So this is a u and this is a v that we can treat. So now we should be able to go through and figure out u and v and their derivatives and substitute back in here. So again, I'll do it as a bit of a side step. So u, it's actually the same as what we considered for u before. So its derivative is still 3x squared, but v has now changed. Sorry, x plus 2 to the power of -1. So, taking its derivative, we need to essentially apply the chain rule, and I'm going to do like the shortcut method. So our inner function is going to be the x plus 2. So if we take the derivative of v with respect to the inner function, we're going to essentially apply the power rule on the outer part. So we're going to get -1 times the 1 out the front, which is -1 over all. We write out our inner function, and we take 1 off the power, so it's going to go to -2. Then we would need to multiply by the derivative of the inner function, which is the x plus 2. And in this case, the derivative of x plus 2, it's just going to be 1 from the 1 that sits in front of the x. So times 1. Nothing really happens with that. So I can rewrite this now a bit nicer. I'm going to go -1 times 1. It's just leaving us -1. And I'm going to put this back on the bottom line. So we get x plus 2 to the power of 2. We know that when we go from top to the bottom line, we change over what that sign is on the index. So that's my u and my v sorted in terms of their derivatives. So let's now go and actually apply the product rule. So this one here is going to give us the overall derivative of the function. So our function was called a. So I'll call our derivative a dash. So it's uv dash plus vu dash from the rule. So substituting in, and v was, well, it was this, or alternatively, we could write it as x plus 2 on the bottom line. All right, so the power, when we swap it down to the bottom, goes to positive, and it's kind of implied that this is all now to the power of +1. So when I sub it in, let's pop it in as the nicer version, and this needs to be multiplied by u dash, so 3x squared. So we'll do a bit of cleaning again and try and make it look like this one over here. So it's going to be -x cubed plus 4 all over x plus 2 squared. This one, we've got the 3x squared times 1 on the top line and x plus 2 on the bottom. Now we can see if we're trying to make it look like this one's got just one kind of fraction, all right? It's got this common denominator amongst everything. So we want to try and get the same common denominator amongst our fractions so that we can join them all together into one. So if we need the bottom line to look like x plus 2 all squared, we've got it here, okay, that matches, but we need to do it also here. Now how we can do that is if we multiply the bottom line by x plus 2 times x plus 2 is going to give us this. But in order to make sure that we keep our equation equal between the lines, we need to have the same thing on the top line. So now it's like multiplying by 1, because whatever's on the top line is matched by the bottom line, and they essentially cancel out with each other. So it's the same as multiplying by 1 or doing nothing at all. So I'll expand this out. So we're going to get -x cubed minus 4 all over this. And then here, we're multiplying, I'll put in brackets so we don't get confused, 3x squared times x plus 2. So we do need to expand the brackets. So it's going to become 3x cubed plus, 6x squared all over. I'm just going to join these together and put them all to the power of 2. So now that we have this common denominator, we should be able to put our fractions together. So we can read across everything that's on the top line. And the bottom line is that common denominator that we're putting together. So we can clean this again. We've got a -x cubed and a positive 3x cubed. So overall that gives us 2x cubes. We've got 6x squared and we've got -4. Bottom line I'll leave the same. And what we should find is that this here matches against what we had previously, and I think that we've got that. So that confirms that we've found the derivative via both methods to be exactly the same. So in this case, obviously, I think it's a bit easier to try and apply the quotient rule, all right, because it's already kind of dealt with the fact that we had to shift things between the top and bottom lines. But just be aware that if you do ever want to check your answers using a different method, the product rule is available for you. It just means a little bit more switching between top and bottom lines as we saw here. So that's all I've got.